Okay, in the last class we discussed about stereographic projection. Okay, I mentioned that the use of it is that angles or angular relationship in 3 dimensions is represented in a 2 dimension. Okay, the advantage it has is that like orientation relationship between crystals we can find out. Okay, angular relationship between different planes. Even when we wanted to projection of symmetries, that could be done in stereographic projection. Similarly, when we wanted deforming a single crystal, okay, how the various slip planes are oriented, how they shift from one orientation to another under application of stress, all these things could be determined using a stereographic projection. Okay. I will come to that maybe later on some of these applications which we will take it up. Okay. Whatever I have told in the last class is just what is basically, what is the basic minimum thing which is required, okay, to construct a stereogram, okay, and I have told that how the different poles, okay, which are intersecting the sphere gets projected in 2 dimension, okay. That is what will be required when we talk about symmetry, okay. What is symmetry? What is the definition? He said that symmetry is a type of invariance, that is by application of some transformation, okay, that could be a translation or it could be a rotation or a reflection or an inversion, we find that the structure looks identical to what it was earlier. That means that we are not able to differentiate between what the structure was. This sort of symmetry is there even in mathematical equations. Okay. Can you tell me an example of mathematical equation where symmetry is there?
Equation of circle passing through origin, center as origin.
Center as origin. Parabola, y equals x squared. Okay. It has a, whether x equals positive you take it or you take x to be negative. It does not matter, the value of y does not change, correct? So, around an axis, if this is x, right, this is a graphical plot of a parabola, correct? So, what is the symmetry it has? It has got a rotational symmetry around it, correct? You take whatever be the value, it will be there. Okay. So, many mathematical equations have got symmetry. When symmetry is described, sometimes these equations are used to represent them also. Okay, okay, that is not the what is part of this lecture. Okay. So, when we talk of this sort of invariance as far as crystal structure is concerned, okay, there are few types of transformations which we can consider. One is translation, then rotation, then reflection, okay. Then we can have inversion, okay. There are under all these transformations, okay, if the crystal looks identical, then we say that there is some symmetry which is associated with it. The translational symmetry, one dimensional periodic lattice, if we try to look at it, okay, like this one, this is, it is getting repeated, so there is a one dimensional periodicity is there. Suppose I shift it from here to this position, okay, then it looks identical. We do not know whether this transformation it has undergone or not, okay. So, we say that it has a translational symmetry, correct. The other symmetry which we talked about is rotational symmetry. Can you give me an example where you have played in a toy which has a rotational symmetry?
Wheel with spokes.
Wheel with spokes. Merry-go-round you have seen, where the horses will be there. You sit on that you look at it anywhere, it has got a rotational symmetry. So, there is an axis, that is what has shown here, there is an axis, okay, around which, okay. What I have done, it is taken one motive R, okay, and it has been placed at this point, okay, then if we rotate it by a specific angle, okay, this R repeats itself. This R, if this should have a symmetry which is associated with it, having one motif here alone is not sufficient. When we rotate by a specific angle, at all positions that motif should be there, and which should be identical with this one when it is rotated and brought here. That is what you can see here. But here if you see the number of R which has considered, the motif which is considered, 8 are there, correct. As far as around the axis if we consider, we can have any symmetry associated with it, okay. If we wanted to know what all the positions of this R, okay, that is what I have given here, that n-fold rotation is possible. That is whatever be the value of n if it is not consistent with translation. If it is consistent with translation, there are some restrictions, right. Suppose we wanted to find out the position of R, if we go from here to here, this motif, how do we find out? To go from one position to another position, if we wanted to find out that, what is the way in which we can do it?
Since they are equidistant, we can say how much angle it has rotated.
The angle you have rotated, but mathematically how do you transform into it?
Angular displacement.
Angular, this can be done using a coordinate transformation. Suppose we take two axes, this is the original orthogonal axis and it is being rotated, okay. If we know the new position, what is the angle which it makes, like this x1 coordinate makes with x, y and z. Similarly, we can find out what the angle if it makes, okay. The relationship will be that x dash will be equal to x cos angle between these two, that y cos beta plus z cos gamma, correct. This can be easily proved and verified. So, using this set of linear equations, okay, we can find out what is going to be the coordinates. That means that we have just rotated the coordinate by some angle, right. This is equivalent to, suppose some point is there, it has coordinates x and y, okay. If we rotate that also, the same type of a transformation which takes place, so it will give the position of the new coordinates, okay. Similarly, if you wanted to come from the new coordinates to a old coordinate, this is the same transformation, which normally we write it in this form, okay. Suppose we wanted to find out, okay, one-fold rotation is only there. How will you go about and find out? Suppose an axis system which we have chosen, okay, only a 360-degree rotation around Z axis is possible. Then what will happen to the axis? Axes are all identical, correct? Then what will be the angle which this x dash axis makes with the x? 0. But with respect to y, 90. With respect to z, 90. Now if you substitute it, what will happen here now? This will become x dash will become x, y dash will become y, z dash will become z. That means that they are identical to itself, correct? That is the way we can find out, okay. This is essentially what is being written in a matrix form, we can write it, this transformation matrix, where these are all only the cosines of the angle which are involved, the matrix. The same transformation, suppose we think that it is essentially a two-fold rotation is there, then what is going to happen? If a two-fold rotation is there, intuitively what you can think of, that is, if it is x, y and z is the point, okay, after rotation it will become minus x minus y z, correct? Is it not? That is 180-degree rotation if we do that with respect to any point x, y, z, okay. Z remains that same because we are rotating around Z axis, So this will come back to this opposite side. So x and y would have changed, z is remaining the same. Now we know what is going to be the angle, okay, between that new axis. Suppose this is, we call this as x dash, y dash, z dash. Then we can find out angle between them when you know the angle of rotation, correct? So this expression essentially tells about any angle of rotation which we can make it around any axis, correct? This is the most general formula which we can use it to find out the coordinates of a point which are related by a symmetry operation of rotation, correct? Is it clear? Yes. See, you see this. Has it got a symmetry associated with it? What do you mean by symmetry? A point corresponding to it, there is another point which is there. Suppose the coordinate of this point is xy. What will be the coordinate of this point? Minus x minus y. This by intuitively you are telling. What we have done it, since it has a symmetry associated with it, if I rotate it by 180 degree, the point which was there earlier has come here. So its new coordinates is minus x minus y. How do you find out that coordinate? By using the transformation. That is, either we can keep the axis fixed and from rotation from one to the other we do, or essentially it is equivalent to if we rotate the axis around the z axis by 180 degree, that also will give the same equivalent results. Okay? That is the way we can find out mathematically. Because in many books these all values are given. Okay? In the international crystallography table, these values are readily available, but this is how it is generated. This is the matrix. And in any coordinate transformation which involves rotation, okay, where that origin remains the same, this is the sort of transformation. So this way, suppose we take an angle of 45 degrees, okay, the rotation of the axis around the z axis or any of the axis, then we can find out what will be the coordinates of the various positions which when we give a rotation of 45 degrees, okay, it will be essentially 8-fold rotation, correct? What will be the position of each of the point, their coordinates we can determine. That is what essentially I had just given the transformation matrix here. If you have an only one-fold rotation, this is the sort of a transformation rotation matrix which we will have. If you have a 180 degree rotation, then if the matrix is so if you take that, it will turn out to be, the coordinates will become minus, right? Similarly, if it is a 4-fold rotation is the operation which we are performing, this is the sort of a matrix which will come, okay? Okay, these things slides I will, no, in fact I want you people to work out all these things, then you will understand much better, okay? You just listen. So far what we have considered is only just how to go about and find out the coordinates of different points when we are doing a rotational symmetry operation, correct? And this is around any axis which we are considering it. Quite often when we have a lattice, if you are looking at around an axis, a rotational symmetry, that symmetry should be consistent with all the lattice point or translation also, because after the rotation every point should come back and should be coinciding with another point, correct? Then only we can say that the structure is identical position it has reached. That means that the rotation should be consistent with the translation, okay? Just I have taken a rectangular lattice, okay? This lattice I had just rotated by 90 degree, Okay. This is how it looks like. I had just shown this projection so that this tells that there is a rotation which has been given to it. Okay. Now, if I try to superimpose these two one on top of the other, okay, you find that the lattice point positions or the atom positions do not match at all, correct. That means that this 90-degree rotation is not consistent with this lattice. Okay. I have rotated this by 180 degree. Okay. That is why you can see that this position which was there, which was here initially, now has come back onto a top. Okay. Now, if I superimpose these two structures, now you see that they are matching perfectly well, right. So, 180 degree rotation for this particular crystal structure is consistent with translation, correct. That means that in crystal structures, when we consider all angle of rotation is just not possible, does not give rise to symmetry, that is rotational symmetry, okay, for any angle of rotation, okay, is not satisfied for periodic lattices, So, what we will do is that what are the type of symmetry elements, okay, or rotational symmetry which are possible in 2D lattice, which we will try to look at it. Okay. This I explained in the previous class, that essentially what you do it is you take a lattice, okay, each of this lattice point we rotate it by an angle phi, okay. We assume that it comes to another lattice point. So, if they reach another lattice point, this distance should be an integral multiple of t, that is what we have taken. So, this is going to be nothing but t plus 2t cos theta for any value of m, can be any value which it can take. That means that cos phi will turn out to be this angle turned to n minus 1 by 2, or the cos phi equals n by 2, okay. M minus n 1 we can take it to be n, but we know what is the value phi can take, minus 1 to plus 1, right. That is the maximum value which it can have, eh? Cos phi, okay. No, cos phi can have minus 1 to plus 1, that phi can take value from 180 to 360, right. Now, what are values of n for which these are possible, that is what is given in this table. Okay. It immediately turns out that 1-fold, 2-fold, 3-fold, 4-fold and 6-fold, these are all the only rotation which is consistent with translation, right. Whether it is a 2-dimensional lattice or a 3-dimensional lattice, the rotational symmetry only these which a crystal can have, a periodic crystal. Is it clear? Suppose we consider a reflection, because that is also another type of this one. So, a hand which we can, there is a mirror symmetry which it comes. Many crystal lattices, it can so happen that one can have molecules which are sitting at different lattice points, they themselves have some mirror symmetry associated with it, because of which the lattice itself can have a mirror symmetry associated with it. Okay. This is just an example of an object which we have taken, put a mirror, it is getting reflected, correct. So, this mirror also how do we represent mathematically? That is, if we choose the coordinate system such that this is x axis, as I mentioned this is y axis and z axis is normal to it. So, along this x axis, that is on the x z plane, okay, mirror if we keep it, then what will happen? That for a point x, y, z, the x will remain that same, y will become minus y, z remains that same, correct. So, this is how the transformation will take place. Okay. This can be written in the form of a column matrix, then this is going to be the transformation matrix for reflection. Okay. This is around the mirror lying in the x z plane. The mirror can be along the lying on the YZ plane also, right? If it is lying on the YZ plane, what will happen with the coordinates of the Z? It will turn to minus x y z. This is how it will transform. Okay. The transformation matrix will be this is what it will be, correct? So using these transformation matrices, we can find out the position of the coordinates. That means that if we know the symmetry elements which are associated with a crystal, and if we fix a coordinate system on any point, we can find out using the mirror symmetry what all points or what all positions in which the lattice should be there if it is we are looking at the symmetry of a lattice, or if we are looking at a crystal structure, what all positions in which the atom should exist in the crystal, that information can be generated. Okay. This we will take it up as example later, and we will do some classwork, okay, as an assignment. Then here if you see, this is with respect to, we have considered only a just an object, okay, looked at the mirror symmetry. Here we are showing a two-dimensional lattice. Not two-dimensional, one-dimensional lattice. So in a one-dimensional lattice, I can keep a mirror here, okay, and then I put a mirror, then you find that or at any point, okay, then all the points will be brought to an identical position. Okay. So this is one position we can keep the mirror, or in between the lattice points at the middle of it, if we keep it also, okay, it satisfies the mirror symmetry. So what we have considered with respect to an object is with respect to only one position. But in a crystal, when we keep a mirror on one of the lattice point, because of the translational periodicity, we find that there are at other positions also where the same type of a symmetry operation leaves the structure unaltered. With respect to a two-dimensional lattice, if we consider it, okay, there is a mirror which is kept here, that is a mirror which is in this one. Now we can see that in between there are two types of mirrors which are coming because of the translational periodicity. You understand that? Here you can see that that is what I had just shown here, how it is coming. Okay. What is inversion symmetry? If we have a three-dimensional, that is like here, okay, if there is any point is here, okay, and its coordinates are x, y, z, okay, this will transform to, if there is another identical point, okay, which has coordinates minus x, minus y, minus z, then we say that they are related by inversion. Okay. Inversion also, that is a question which arises whether inversion symmetry, is it a pure symmetry operation or whether it is a mixture of it. It is essentially, if you do a rotation, that is like for this hand, if I take rotate it by 180 degree, okay, and then I put a mirror perpendicular to it and take it, okay, then what it happens, that it is a combination of two symmetry operations, rotation and reflection, okay, that gives rise to inversion. Here also we can write a transformation matrix for this operation. So far what we have considered are what are the type of symmetry elements which are possible for a periodic arrangement of crystals. Translation symmetry, rotation symmetry, reflection symmetry, okay. These are all the symmetry, or a combination of rotation and reflection is there. Reflection and rotation and reflection, or rotation and translation, reflection and translation, or a combination, all are possible. Okay. If different types of symmetry elements are present, okay, suppose there is an axis of rotation axis is there. So around this axis, if I do a rotation symmetry, what is it which is going to happen? The point on the axis will remain unmoved, correct? All other points gets rotated, okay? So with respect to only if only one symmetry element is there, which is a one rotation axis, okay, all the points on the axis remain unmoved, others are shifted. Suppose there is a mirror which is cutting it perpendicular to it, then what will happen? If both the operations are there, where they intersect, that point is going to be unmoved. All other points are shifted during the symmetry operation, okay? Since one point remains unmoved, these sort of operations are called as point group symmetry operation, okay? There are other operations are there like screw axis as well as a glide, okay, where all points are shifted, nothing is remaining fixed, okay. So this operation, point group operation, where that's why this point group operation is called as a symmetry operation, where all these symmetry elements pass through a point, single point, and that point remains unmoved, okay. And why study of symmetry, point group symmetry is important? Because all the properties of the crystals, okay, externally if you look at it, they exhibit a point group symmetry, that is all the symmetry elements pass through a point, okay. So whatever the properties which we determine, like either magnetic susceptibility, okay, or if you are looking at the external forms of crystals, okay, what we can see is that whether a glide is there or a screw is there, we will not be able to make out. But whether there is a reflection is there, rotation is there, okay, or inversion is there, these are all the things which we can see, okay. So they will all be intersecting at a point. So this is called as a point group symmetry, because that's what we are, that's a property which we measure, okay, or we are able to observe, okay. Let us consider the case of up to this it's clear, the concept of rotation symmetry, reflection, inversion we have considered, correct? And what are the ways in which it can be represented, the coordinates when we do this operation, that also we have looked at it, okay. Now let us look at one dimensional lattice. This is just an one dimensional lattice which we are considering it. In this lattice, when you look at it, what is the sort of rotation symmetry which you can think of? What do you see here? Rotational symmetry. Translation is anyway it's going to be there. Only 180 degree rotation, correct? That means that a twofold rotation. If I rotate it by 180 degree, it comes to a position which is identical, but when I rotate it again by another 180 degree, all the positions come to a original position which they were occupying earlier. That's what I had shown, right? Now they have come back to an identical position. That means that one dimensional lattice has got, all one dimensional lattice, two periodic lattice has got twofold rotational symmetry. The axis is on a point which is on a lattice point normal to the screen, correct? Or I can take an axis which is midway between these 2 points, lattice points, anywhere. Then also if I take a rotation around this point, if I take a rotation of this one, again it will come back to identical position. So there are 2 points are there as well as this. Like that I had just shown as an example these 2, it could be everywhere it's going to be there, right? Any of this point if I try to rotate it. Looking at this figure, we will think that suppose you take it here, we rotate it will be coming towards this side, because by definition lattice is infinite, correct? So what we are showing it is only a very truncated small form of the lattice, correct? So this has got a twofold rotation. What else you see other than a twofold rotation? Anything else which you can see in this? Any other symmetry operation? Mirror. Yeah. That is, if I put a mirror here, okay, or anywhere on the lattice point, okay, it will come to an identical mirror reflection. Or if I put a mirror midway between, okay, lying on the XZ plane, then also it will be, right. These are all the positions which, suppose I put a mirror here, then what will happen? See, now you see that this, when it has rotated, this shows the position which it is occupying. They are not coming back to an identical position. That means that there are, once a lattice is fixed, there are specific positions only at which symmetry operations are possible. All other positions, the only type of a symmetry operation which is possible is only one fold. Right? At this point, if I give an one-fold rotation, that is 360-degree rotation around it, it will come back to an identical position, but there is no other symmetry operation which is possible. So, even in a lattice, when you look at it in 2-dimensional or 3-dimensional lattice, once the lattice points are fixed, there are specific positions in the lattice only these points are called as special points, okay, which will come later. Okay. This is what. So, just similar to a unit cell in 2 dimensions or 3 dimension, 2-dimensional or 3-dimensional lattice. In 1-dimensional lattice also, from here to here is what the unit cell is going to be, correct? Okay. And these are all the symmetry operations which are going to be there. Okay. So, in this 1-dimensional lattice itself, we have a translational symmetry, a two-fold rotation is there, a reflection is there. So, what are the symmetry elements which it has got? It has got a 2M symmetry, correct? These are all the symmetry elements which a 1-dimensional lattice has got. This is only a lattice which we have considered. Suppose we wanted to, yes.
So, isn't rotation and mirror the same operation?
Which one?
So, rotation and mirror in a 1D lattice would be the same operation, right? Because XYZ will become, sorry.
No, any operation which you do, whether it's a reflection, any crystal structure, it doesn't, even in a 3-dimension, okay, all symmetry operations should bring one lattice point to another point. It doesn't matter whichever be the operation which you perform.
So, your mirror and rotation are the same operation. They your X will become minus X. In rotation also X will become minus X, right?
You will just see when you put a motif. Okay. As far as the lattice is concerned, the lattice point has got infinite symmetry. Okay. Now, what we have to see it is that suppose you put a motif, what will happen? Okay. So, this is just an 1-dimensional crystal. Now, I place a motif which is an asymmetric motif. I choose it to be P as a motif. Okay. I place it here, and at all positions it has been placed like this. Now, what is this symmetry which this crystal exhibits? Only one fold. All other symmetry elements are lost, right? So, the symmetry which the lattice exhibits is the maximum symmetry which the crystal can have. But generally, now you can make out, right? It is not the. So, once you place motif, depending upon the type of motif, okay, the symmetry elements will change. We will come back to it in some cases identical, but in many cases there is a difference between reflection and rotation. Okay. Though this right hand and left hand look like 180 degree, if both have got identical infinite symmetry, then only it will be. Otherwise, like here also if you look at it, 180 degree rotation will bring it like this, na? They do not come to an identical position if you put an object. That is why when you put a motif, you can see the difference. Here what we have done it is, okay, we have chosen a motif which is P, okay, an asymmetric motif, and another around this point if I look at it, there is a 180 degree rotation, that is two-fold rotation is symmetry is there. I place this motif around each of the lattice point. Now what all symmetry elements which are there? Along the x-axis, if you now try to look at it, there is no symmetry. There is y, there is only one fold. Z, that is around the Z axis, there is a two-fold symmetry is associated with it. So that is how it is there, the primitive 1, 1, 2. This is how it is. Here it is primitive, all symmetry along all the directions are 1, 1, 1. Now you look at here. Here I have chosen a motif P. This is mirror related. If I place this motif, now you see that with respect to the xz plane, okay, that is a mirror, others are all one fold symmetry, correct? Now I am choosing a motif where P, it is reflected across this. Now what it has? P1, along the y, there is a mirror symmetry. In other two axes, there is only one fold rotation, correct? Here it is along the x axis, so these are two different structures, correct, crystals. Here, now what has happened is that this has a two-fold rotation around it, and there is two perpendicular mirrors are there on x and y, so it becomes MM2. Okay. This symmetry, if you look at it, around a point, okay, all the symmetry elements either intersect or there is one axis of symmetry which is there. So this is essentially are all point group symmetries. Okay, one point remains unmoved. So in one dimensional lattice, we can have 5 types of, like space group lattice we consider about, we tell that there are 230 space groups. Similarly, with respect to point group, if we consider, there are 5 are possible. Okay. Is there anything else which is possible? That is, a glide is also possible. That is, if I take P, okay, from here to here is the lattice translation vector in this one dimension. Now, if I move it half and take a mirror reflection, it will come to this position, correct? Again move it half, mirror reflection. So this is a glide. So now what we have is that around x axis only one fold rotation, Z one fold rotation, a glide along the y axis, and there are some symbols to represent the glide. This is called as a B glide on y axis, that is why I had chosen. These aspects of it will come later, but what you have to understand that this is another type of a crystal which can be constructed. The third which we can do it is that we have this one. This is also can be, instead of a mirror here in this one, we can have a glide operation. Then this is shifted by half, then reflected, again shifted by half, reflected, it comes back to original position. Okay. So here there is a mirror along x, correct, on the xz plane. Then along the y direction, we have or the y z plane, there is a glide, okay, and then on the around this point, if we consider, there is a two-fold rotation is also there along the z axis. So these are all the symmetry elements. Here what happens is that all the points are getting shifted because of the glide which is associated with it. Okay. This we can call it as equivalent of the space group. So the total number of equivalent of space groups in 3 dimension 230 we have. In one dimensional lattice, we can have 7 groups can be there, point space groups. Okay. So looking at this one dimensional lattice itself, you have got an idea of how the various symmetry elements come, correct? Concept of a lattice, what is the difference between a lattice and a crystal? Okay, some idea you have got it. symmetry elements like rotation, reflection. Not all symmetry elements you have seen, but some symmetry elements you have seen, correct? Glide you have seen, reflection, twofold rotation. These are all the aspects which you have seen, correct? This is just I had given some example. These are all from all the border design. If you look at it, they have some symmetry associated with it. One dimensional symmetry is always there. Okay. Here this is one which has an only one fold rotation is there. This is another structure. This you look go to any cloth shop and look at all the saris or border which you have. You try to find out what symmetries are associated with it. That's the best way to learn. Okay. So various types. Here I had given some patterns. Okay. You can try to find out what all types of one dimensional symmetry which is associated with it. That will give you how to identify. That's to identify the symmetry, first thing what you have to do it, because so far what you have done it is, we know a lattice, we are taking a motif and trying to generate it. Now we have come to a reverse problem. We have a pattern which is there, periodic pattern. Now we have to identify what is the motif which is there first, and then how the motif gets repeated. When we try to identify it, then we will be able to get what are symmetry elements which are awesome. That is what actually the real problem is always, correct? I will just mention briefly about two-dimensional lattice and then we will stop. Okay. So far what we considered is only a one-dimensional lattice. Okay. What are symmetry elements which are associated with it, and we saw that 5 point groups crystals can be there, and space group crystals, if we consider in one dimension, there are 7 are possible. Let us try to look at what all types of point group symmetries which we can have, okay, with respect to two-dimensional lattice. Okay. Like we consider the point group, okay, there are around every point. Here also, like the symmetry operation, rotation, reflection, okay, or an inversion, these are all the operations which will intersect, will leave some point or an axis or a plane, okay, unmoved. Suppose we take a motif R. Okay. What is being shown is, this is taken from this book, Christopher Hammond's book on crystallography. It's a very nice book, okay, edited by International Union of Crystallography. You take a motif R, okay, what symmetry which it has? Only one fold rotation, correct? That's why you call it as an asymmetric motif. Other than one fold rotation, it doesn't have any other symmetry. This is also a figure which you see. This is taken from an art. Okay, you can go to an art museum also look at it. Many of the drawings which are there, they have this type of symmetries are associated with this. Various symmetries one can understand. This has only a asymmetric, and this is another molecule which is being shown, okay, which I had talked about in the first class. It has got only one fold symmetry which is associated with it, right? So in various walks of life you can always see that is symmetry is a manifestation of nature, but symmetry does not become nature, it is only a manifestation. And if you take R and put a mirror, it gets reflected, right? So you can see this structure here. This is a difluoroethane. This has got only a mirror symmetry which is associated with it. And similarly here, if you see it, it has got a mirror, 2 perpendicular mirrors, and a two-fold rotation is there. Okay. So you can see that 2 mm. Okay. Then this is a two-fold rotation is there. This is putting a asymmetric motif, okay, around this axis if we see. When it comes here, so similarly you can see a 3-fold rotation here. Okay, this is, then you have a 3-fold and a mirror. Okay, then how the structures will look like. Okay, that's for boric acid, this 3M symmetry. Here just a 4-fold is there for this structure. This is one of the, I think, rangolis which people draw, the various shapes. This has 4-fold. Here you can see that it has a 4 mm symmetry. Okay. Then this is a 6-fold. Okay. Then here it is 6 mm. 10 plane point groups, because we know that rotational symmetry 1, 2, 3, 4 and 6 are possible. Then mirror is another one, because in 2 dimension we can't have an inversion because a space lattice is required. So that becomes 7. Then a combination of this can be taken. So when we take the combination, 2 mm is one which it comes, 3 mm is one comes, 4 mm, 6 mm. If you add all together, we have 10 types of plane point groups are possible. These different point groups can be represented in different methods, okay? Because whatever I talk about here, that's exactly the same way it is done for a 3-dimensional lattice also, okay? One is by like symbols which we used, 1, 2, 3, 4, 6, okay? Then another is a combination of 2m, okay, 2mm, 3m, 4 mm, 6 mm, like that. Then the other is there is Schoenfly symbol is there. I think that's the symbol which there is C1, C2 like that, then D with dihedral. There are many ways in which it is represented. That's another method. Mostly people who work on material chemistry people, they use not Hermann-Megwin symbol, they essentially use the Schoenfly type of a symbol, okay. Then a stereographic projection with which it can be represented also, all this symmetry, okay, that I will show that. Then each point, when we do a symmetry operation, equivalent points are generated in the lattice. Those points with their coordinates, we can represent them, right, coordinates of the points, that is one way. The another is that using the matrix transformation, the coordinates of the points, we will have the type of specific transformation matrix for each of the operation of transformation with which we can do that. Or we can draw actual crystals and look at it also. These are all the various ways in which we can represent it. Like different symmetry elements which we have looked at it, I will give us assignment to work out for different structures how the points are generated, okay. That when you do that, it will become much clearer to you people, okay, how these symmetry elements. We will stop it here now.